What I want to talk about here for a while then is this is going to be some of the nuts and bolts and then how we actually go through our calculations with Water Optimizer, what's involved in getting these estimates. You know, what I want you to get out of this is basically how we do it and maybe get a little bit of assurance that what we're doing is reliable. And so we'll show some comparisons to some field data, and we think that we're certainly, you know, it's reliable, the method that we have. This is Water Optimizer, and really the purpose that we have is I want to describe the principles for analyzing those planning decisions with deficit irrigation. That's kind of going to be what the goal of this particular session is. You know, these things that have led us to groundwater, to deficit irrigation are listed here. I guess I kind of hit those a little bit earlier. And all of these are playing out in a little different form of allocation. And so I'm not going to walk through all these, but all of the NRDs generally have some differences in what they do, how they look at using a CREP, for example, and other areas like that in terms of managing that water balance. So Water Optimizer, right now it's a program that's written into Excel that you can download off the internet. It has a lot of pieces in it that you can analyze various parts, both for water limited, and even if you don't have limited water supplies, you can look at that optimal irrigation depth. And some of the questions we focus on is which crop should I irrigate? How many acres should I irrigate? What net return might I expect? What are the trade-offs between yield per acre and the amount of land that I irrigate, and which ones of those may make the most sense there? We view this as a method. If you were to run the program, we would view it as a way for you to compare alternatives. We're not going to propose that we have the exact one answer. We don't want you just to run this once. We would want you to sit down and analyze a comparison of, say, 3 or 4 or 5 alternatives that you might want to look at. Now, the handout that you have is kind of a summary of how this all works. I'm not necessarily going to go through that handout piece by piece. It's just kind of a part that you could read on your own maybe. It kind of overlaps some of what I and Dr. Sapalo are going to visit about here the next 2 or 3 sessions. So deficit irrigation, one type of decision you have to make. Let's suppose you had a water allocation of 10 inches of water and you had a 130 acre pivot. How am I going to spread that? So I got 130 acres times 10 inches. I've got 1,300 acre inches of water. How am I going to spread that water across that pivot? So maybe 2 alternatives. One alternative would be that I could look at irrigating that whole field and spreading the water uniformly across that field. The other option might be that maybe I'd irrigate 100 acres of that field and I'd have 30 acres that would be in my best dry land or rain-fed cropping practice alternative for my region. And so what we want to know, in this case, we'd only irrigate maybe 78% of that land area. And so what we want to know is, you know, which one of those might be the more economically attractive, or are they even really that much different? So we're looking at some of the relationships we use to get to that. Okay, you guys are getting nauseous looking at linear yield ET lines, I get it, but it's really the heart of what we do. We know that for all the crops we look at, Gary showed you data that supports the idea that we have a linear yield ET line. So on the upper point here, on the upper right-hand side would be what we call a full yield. We used to call that maximum yield, but some people maybe misinterpreted what we meant. What we mean is that's a yield that you could achieve if you irrigated well in your field. This is not the yield that the person's in the yield contest is going after here, okay? So this is something that you can expect to achieve out there in the field with good management. When I don't irrigate my irrigated crop, like in Gary's treatments, when he didn't irrigate some of those crops, you still generally would get a yield. And so what we see here is that's kind of this non-irrigated yield that we call it the subscript sub n. If we take this line and in a particular year, maybe my non-irrigated yield, maybe I've got, in this case, about 70 bushel of corn. If I extended that line down, it didn't actually happen in that year, but if I extended that line down to like a year like 2000, you would reach a point, an intercept here, a point where that's the amount of evapotranspiration you'd have to have for corn before you got any yield at all in this particular location. And so why, in this case, you'd have to have 12 inches, maybe 14 inches of ET before you got any yield. Well, did we see that this last summer? Did you see a lot of fields that got waist high and burned up out there that were dry land this last summer? A lot of places around the state you did. And so obviously that crop that never got to a grain fill stage of growth used some evapotranspiration. That's what we mean by this intercept here that we have on this axis. And there was a question I think Mike might have asked it a while ago about what's the difference in crops. And I'm going to try to come back and show that curve that Gary said existed here in a minute. The other thing that we're seeing then is this yield, the slope of this yield ET line for corn is varying from 12 maybe up to 15 bushels of corn per acre inch in some of the experimental work that we're doing. It is really steep, and it's one reason that corn is so dominant. Besides the nice prices we're seeing, it's really the main reason that it's so dominant in terms of being an alternative for us in terms of being one of our better choices. This is some data actually from a series of experiments, and you can see again, in this case we have an excellent fit of yield versus ET to corn data. In this case we had about 13 bushels, a little over 13 bushels of corn per acre inch of water from field experiments, and it took about 12 inches in this location to produce of ET before I got any yield at all. What we find out is that this amount of ET that it takes before I get any yield at all depends on how humid the environment is that you operate in. If I'm in eastern Nebraska where I get a significant amount of rain early in the spring, I have a lot of just evaporation off the soil. As compared if I go to where Gary's at Scotts Bluff, that evaporation off that soil is a lot less out there. So what we see in eastern Nebraska is that this intercept is bigger than it is out in Scotts Bluff because they don't have that pre-season evaporation that's going on as well. So the slope of this line is not constant as you go across Nebraska. That slope's going to change, and it's frankly going to get steeper as we go eastern Nebraska, and it's going to get a little flatter when we get out in the Panhandle. And so we try to build that in and account for that variability as we go across the state. We also have worked a lot with Norm Clockey, who's a colleague, was out at North Platte for many years and then moved down to Garden City, Kansas, and Norm has run a lot of experiments of water stress. So this is taking 5 years of data that Norm had, the way Norm showed it. This is all corn grown at Garden City, Kansas from 2005 through 2009. And if you fit the line through all of the years of data, just one line through 5 years of data, usually we fit the line through 1 year at a time. But in this case, if I just do it for all these years, I still get a pretty good correlation. And I'm looking here in his case at about 12 bushels per acre inch. I could show you many more slides that would show this same linear relationship is quite reliable for the crops we're going to look at. This is the slide I think Gary was thinking about in looking at the difference then between different crops in terms of this yield ET line. Now this is actually from some of the data that Gary and his colleagues did out at North Platte in the 80s. The slope is steeper today, not because we necessarily have more ET, but what's your maximum yield today versus in the 1980s? How much has that yield went up? A significant amount, right? And so these curves have gotten a little steeper over time. But in 1980, you can see corn was by far the steepest. At North Platte, it took about 10 inches of ET before you got any yield, and then that slope went up very rapidly for corn. Grain sorghum only took about 7 or 8 inches of ET before you got some yield, but the slope of grain sorghum is quite a lot less than for corn. Wheat and soybeans is significantly less. They don't take as much ET to get that first bushel, but the slope of those lines is much flatter. Soybeans competes with corn in a lot of our analysis because of the price difference. I mean, you're going to look at prices of soybeans, maybe 2.5 times corn for those soybeans to come into the mix. This is back to your question, Mike. I think it focuses on that relationship of crops. Well, we have to get, in order to look at how you manage water, we have to get to this diminishing return curve for yield response to water. And when we put on just the first unit of water or two, I can put on a half an inch of water with my pivot in the evening sometime, and I can get all of that water to go to ET. So the slope of this line is about equal to the slope of the yield ET line for those first few inches of water if I only put on a half inch of water for the year. As I increase the amount of water I apply, I reach this diminishing return where I get a lot less yield for each inch of water that I put on that crop until I get to a point we reach a full yield. And at that point, we need to know what that number is. So this number would correspond to good irrigation scheduling. If I put more water on, generally in Nebraska, I don't suffer yield reduction. If I leach a lot of nitrogen, generally we just put a little more nitrogen on, so that's not so great for water quality, but generally we don't necessarily see a decrease in yield if I over-irrigate a little bit. We don't recommend you do that, but you a lot of times don't see a yield response if you do. So when we look at these two functions together then, these lines are nearly parallel at this low end down here, and then they start to deviate as we go away from that. So when I put a given amount of irrigation water on, some of it goes to ET, some of it goes to these non-ET losses, and our production function provides a way, this relationship between yield and irrigation is called a production function, and it provides a way then to partition that irrigation water between ET that's related to yield and these non-ET losses that don't contribute to yield. How big a fraction is the non-ET loss when I put on just a little bit of water? It's not very much, is it? When I get up here to full yield, those non-ET losses get bigger. So one thing you need to think about is our irrigation efficiency is getting better when I go to deficit irrigation. A higher percent of the water that I pump is going to be used for ET when I'm under deficit irrigation compared to fully irrigated, and certainly if you were over-irrigating the field. So we make these relationships. What if I had an efficient pivot versus a, quote, inefficient system out in the field? Well, to produce the same amount of yield, if I'm less efficient, I have to pump more water. So this slide is showing the case, maybe you're in a location where you don't have an allocation of water and you can pump some more water. I can achieve the same yield simply by pumping a little bit more water. Maybe more relevant to those areas where you're limited on deficit irrigation, I can't pump any more water, I'm limited, but because I become more efficient, more of that water goes to ET and I actually increase my yield. And that's, I think, what has happened a lot of the areas in the Republican Basin, for example, where they've been under allocation for quite a while. They've improved that efficiency because of deficit irrigation, because of management, and because of improving systems. So we try to represent this efficiency in these production functions that we utilize. So what do we need to know? Well, we need to know the yield that we get for our irrigated crop if we didn't irrigate it. Now that means if we're going to have 30,000 plants per acre out there, we need to estimate what that yield would be for that crop for 30,000 plants if you didn't put any irrigation water on. So it's not the same thing as a dryland corn crop. You're not going to plant 30,000, I don't think, many places in western Nebraska for a dryland crop. In fact, your dryland corn is probably going to be in a rotation of some type a lot of the time. So we distinguish between what you would get if you didn't put any water on the irrigated crop versus what you get with a true rain-fed or quote-unquote dryland crop. We need to know the yield when you fully irrigate. We need to know how much water it takes to get that maximum or full yield. And we need to know the slope of that yield ET line. How well do we represent some of these functions? This is a comparison when we do this analysis of some data that was done with Joel Stinkloth and Gary and other people out here at North Platte back in the late 90s. They ran an experiment for 98, 99, and 2000 on surface irrigation. We just looked at the data for 1998. That's about the average year out of those 3 years. So the blue line represents, if you did a statistical analysis to draw a line through the best fit line through that. The solid line here, this black line, is our line that we get from using our production function to represent those yields. And so our argument is that we represent that yield as good as you could do if you analyze the data as a statistical approach. The advantage of our method is we get the production function from physical parameters in the field and don't have to have an empirical data set to come up with that function. That lets us apply this function across a lot of the Great Plains. This is looking at Norm Clockey's data for a 5-year period down at Garden City, then relating irrigation water to grain yield. So there's 5 years of data in here. And as you all know, of course, there's going to be a lot of variability over 5 years, how much yield you're going to get on a specific year. So I'm going to come back and emphasize that we're looking at a planning environment here in the first part of the program today. And from a planning perspective, you should be looking at what's my expected yield, or that means what's my average yield that I'm going to be able to achieve. So if you take Norm's data and you fit a mathematical function through it, you get the solid line. If you use our water optimizer function, where we go in and we simulate all this data without any local field data, we get our kind of center line curve here. We're really close at each endpoint. We predict a little bit less yield than they might measure in the field, but frankly, it's probably statistically these are the same line if I look at how well we represent the data. So we feel like we're doing pretty well in terms of representing those real field conditions with this method. Well, it doesn't do us any good to just talk about yield. We have to get to dollars. And so the values that we're looking at is what we call a net return. And what we're looking at with this would be really what is the increase in income that results from making these irrigation decisions. We're not taking into account This is not a profit. This is not looking at what you have to pay for land cost or taxes or any of those fixed costs that are out in the system. We're simply looking at that variable increase in income that you get by irrigating. Now, I'll let my good friend Ray Sapala correct my definition of net return when he gets to that discussion, but we're looking at how much value you get out of the water. The way we calculate that is we start with a crop yield here, and we multiply that times the net crop price that we think that crop is worth. Now, what's a net crop price? We look at the grain sales price, and we discount off costs that are related to yield. So, for example, if you have a harvesting and hauling cost, we reduce that price sum by what it costs you to do those particular field operations. We also discount off a nitrogen cost that's related to yield. So if you produce more yield, you're going to have a little higher cost than you would if you produced a little less yield. So that's what we mean by a net value of the crop. We look at your irrigation production costs that depend upon the fact that you irrigated that crop. So I had to buy seed, I had to buy herbicides and those things for that irrigated crop. That's a different number than if I was going to do that for soybeans. And so we have to look at those input costs that are related to the fact that you chose that particular crop to irrigate. And generally those are a per acre cost basis. We have to look at the cost of water here. This is what it costs to pump the water, and this is the depth of water that you apply on that field. So that gives us a net return per acre from the irrigated land. We do about the same thing for the dry land, we just don't have that water cost included. Now it turns out the total cost of the water turns out not to be important at all in terms of how we allocate the water, because if we're truly deficit irrigating, you're going to use all the water anyway. So any scenario you use, we're going to be looking at using all of that water. So in the end, the cost of the water is not, it kind of factors itself out. So our total net return then is going to be our irrigated acres times that net return per irrigated acre. It's going to be our non-irrigated crop, which is going to be the amount of the return that we get from those dry land crop that we have in the field. And then we subtract off a startup cost. So what are the costs related to irrigation that you have to pay by the fact you decide to irrigate? Maybe the easiest one of those to think about would be if you're using electricity to irrigate, you have to, a lot of places you have to pay a connect charge, a service charge. Before you pump any water, you have to pay a connect charge, so many dollars per horsepower, right? And so that's a cost that you have to pay. It doesn't matter how much water you pump, you have to pay it anyway. And so there's a few costs like this that are out there that we include into that, what we call the startup cost. So that's how we get to a total net return for one of the alternatives that you would have picked. So that net return curve looks something like this. I'm going to look at a net return curve for a corn crop. This is a crop that it's a realistic simulation of what we do. It's not one that I just drew to make a nice curve here. And so what would be the maximum irrigation depth that you would ever want to apply in this field? 17.5. Why? Well, that's where you get the maximum net return per acre, don't you? Okay. So we would always go to that point. If I had no limitation on how much water I could pump, I would always want to be at that point. That's where I maximize my net return. I want you to think about two terms. One is marginal net return, and that's how much income I increase by the fact I put on another unit of water. So if I put on 1 more inch of water, how much do I increase my income? And we have to think about that, how much do I get for that next inch of water that I put on? The other net return, and maybe the more important one to think about, is the average net return to the water that you have. So what I'm looking at here is how many dollars on average do I get for my quantity of water supply that I have available. I argue that our goal is to maximize that average net return for the water that you have. If I maximize the average net return or value of the water that you have, that's going to be your optimal decision point. Well, that average net return, I'm a graphical guy, you figured that out by now. This would be the net return that I could expect from my non-irrigated crop. So maybe in this case, my non-irrigated, my dry land alternative is an eco-fallow corn wheat rotation. And with that system, we were getting about $100 per acre net return in this particular example. When I look at my irrigated corn now, the slope of this line represents that average net return. This is what I could have had if I didn't use any water on that acre. And this is what I could have if I irrigated up to maybe to 14 inches on that particular point. That slope of that black line is that average net return. Where is the slope of the line the maximum? I got to stay on the blue line. Each little point I pick on that line has got to stay on the line. Well, obviously where that line is tangent to, or where the line just touches, see this average net return pivots about this point, and it goes through whatever point you pick on the blue line. So we're maximum right here. This is going to be our optimal net return. So if I were to look at slope of the line at 1 and 3, it's less than the slope at 2. Does that make any sense? What we're trying to do is find out where that point number 2 is on this curve so that we can maximize the value of your water. Believe me, this is a simple answer to the way this calculation turns out. So what we see here is we have what we call a land limiting. If I didn't have a water limit, but I had a limit on how much land I could irrigate, you would go out there and irrigate for the maximum net return if you were, purely profit driven. If I spread the water out across the entire field and did it uniformly, maybe I have enough water that I could spread. If I put 11 inches on, I could irrigate the whole field. So you end up with this range of irrigation amounts per acre that we're trying to determine in these calculations. What we find out is the optimal water limiting irrigation amount obviously fits between those two limits for the example I have, because my average net return is maximized. There's a range that we look at, and then there's an optimal net return that we're going to have. And you'll see here, if I try to irrigate this field and produce produce a yield in the entire field, my average net return would be a slope from about here over to there. If I went for maximum net return and reduced acres, it again would be less than what you would see for that water optimizing amount. So what we do is we go through this optimization program. It does all this shucking and jiving in this Excel program, really to determine what that optimal water limiting point is for whatever crops that you select. We can look at the yields for different crops related to irrigation. So we go from the ETE to irrigation relationships for all of these crops. We also calculate that net return then for different amounts of irrigation for the different crops in the system. I don't remember how many crops we have, but we have a large number of crops now that you can pick from: alfalfa, soybeans, corn, grain sorghum, sunflowers. You gotta be a little careful with sunflowers. You need to really have good local information to put in there. But there's a large suite of crops that you can pick from if you want to look at those. We have probably a dozen dryland alternatives that you can look at, that you can put in there. And internally, we generate all these curves. You never see these, but we generate all these curves. Let's look at an example then. If we were evaluating crop response to irrigation and we wanted to pick our optimal cropping system, this would be a simulation that I did looking at the amount of water I applied to crop yields. But now instead of just having corn, I've got corn and soybeans. So the green line is showing if I don't irrigate those soybeans at all, I got 70 bushel of corn, sorry. When I irrigate 13 inches, I reach my maximum, and so I got a little over 200 bushels for this particular case for my corn. For soybeans, if I didn't irrigate, I'm somewhere around about 35 bushel, and if I fully irrigated at about 9 inches or so, I get up to about 50, 55, probably 60 bushel per acre of beans. So this is my production function, looking at it now as a bar graph instead of a curve. So here's our net return for corn. Our best dryland alternative for this, again, was a wheat fallow rotation, rain-fed condition. So the best operating point for our corn, the point where that net return that average net return is the largest, it occurs at 10 inches of water. So the optimal irrigation depth for corn is 10 inches. So if I have 1,000 acre inches of water to put on, I divide by 10 and I'd put out 100 acres and I'd go to 30 acres of dry land, eco-fallow. That'd be my optimal point. If I had, if I had 1,300 acre inches of water, I'd divide by 10. I always put the 10 inches on. It's always the optimal for the corn. Let's look at now at soybeans. When I put the soybeans in this case, I see that the optimal depth for soybeans is about 5 inches of water. And guess what? The average return for soybeans is a little bit better than corn. So if you only had an allocation up to, say, 5 or 6 inches, which crop would you pick? You're going to go with the soybeans, right? Because you get more dollars per acre inch of water on the soybeans. So you would stay with, in this case, you would stay with soybeans until you irrigated the whole field with soybeans. And then you would start to make a transition. And this is where stuff really gets kind of interesting. So in this case, if I had a 650 acre inch allocation, that'd be 5 inches on 130 acres. Alternative one would be to put out 130 acres of irrigated soybeans. Alternative two would be put out 65 acres of irrigated corn and 65 acres of dryland corn. If you look at our average net return for the soybeans, it's about $41 an acre inch. Our net return on the corn was about $37.2. So we look at our maximum value of the water is here with the soybeans about $26.6 versus $24.2. So in our program, we would be picking the soybeans in this case. Let's suppose you had more water. What if I gave you enough water to have 1,300 acre inches of water? Let's look at this graph a little bit as we go along. You know, we started out here when we only had 650 acre inches of water. Our optimal was 5 inches on beans, and we would put that on 130 acres. Now you give me a little bit more water, so I could put a little more water on the beans. Well, this yellow point is still above the net return for the corn. So I'm going to stay on that. When I get to this third point, now my net return for corn and soybeans is the same. It's a push. I can do either one and I get the same net return. If you increase my water level one more time, now then soybeans starts to fall off and it's less than my net return for corn. So after I get past this point here, I'm going to begin to make a transition to irrigating corn. And so I'm not making a recommendation here, irrigate soybeans early and corn late. Dr. Spall is going to get to that. But I want you to understand what we do in the program. We look at these alternatives inside that program to decide, you know, which crop would be the optimal at different amounts of water. So as it turns out here, in this case, if I had 1,300 acre inches of water, I would go with 130 acres of corn, or 130 acres of soybeans, and I would make more money in the corn. This is kind of what we do inside there. In order to do this, then how do we get parameters for a model? If we don't go out and run a field experiment, how do we get those values? So what we use is we have a computer program that we use to simulate the water balance, daily water balance of cropping systems. I'll talk a little bit about it in detail. We simulate what happens when we only have rainfall for those crops. We estimate the fully irrigated and non-irrigated yields using a combination of data from the National Agricultural Statistical Service and from our CROPSIM model. So our CROPSIM model does not predict crop yield. We use an independent value for that. From this, we get the slope of that yield ET line. We've worked pretty hard to try to maintain relationships between crops. It's really important that we capture the relationship of one crop to another when we do this analysis. And so we've looked at the reporting from like NASS, and that seems to be one of our best, widest spread basis for getting that data. So we've built a lot of our yield function data on that, and we then end up also have a method that we can develop a relationship for how efficient the pivot is, and I'll get to that one in a minute. So our general modeling approach is we run our little CROPSIM model. It takes information, soil information, weather, crop characteristics, and our production zone characteristics. We run it through the model, and our outputs are annual irrigation requirement, our annual ET for fully irrigated and not irrigated crop, the yield of the non-irrigated crop relative to the well-irrigated crop. We use the NASS county level data to develop estimates then of what our yield would be for fully irrigated and non-irrigated values, and we do this on a county basis. This CROPSIM model, like I say, it's field scale. Marcia asked about, do we look at effective precipitation? And we do that by looking at that SCS or NRCS curve number method to look at what water infiltrate. We would love to have a little better method for that, but that's what's available out there that's widely used today. We look at how much deep percolation occurs. So we're doing these daily calculations on all of these systems. It requires input for climate, soils, and farming practice. This is kind of a little depiction of this crop water balance. Interestingly, I don't know if some of you are working with the Department of Natural Resources or some of the NRDs, they've actually picked this model up, and I know the Central Platte NRD is using this model to look at how much water they get when they retire irrigated lands in some of their initiative to get back to no new depletions, and now the Department of Natural Resources is beginning to use it also for a consumptive use calculator. So sometimes things get used in ways you didn't quite think were right or isn't what you intended, but I think it works there. So we calculate, what we do is we calculate every one of these little blue arrows on a daily basis in the field, and we keep a balance. We look at how much we're changing the happy face on the water here on a daily basis. If we get too much water, we drain it out. If we have runoff, we run it off. And so we run this water balance. We divide the soil into layers so we can deal with different soil types throughout the profile. We define a field capacity and wilting point throughout the profile. And then we simulate the movement of that water pretty much as just based on gravity. We don't have any upward flow component to it right now. Soils, we've done a lot of work to try to get data. We can go now. This is showing using the StatsCo database from NRCS to get input into a model. We've recently converted now where we can look at a CRGO, the more detailed database, and develop parameters. You know, this is the StatsCo soils, and this ends up being the soil code that we use in the CROPSIM model. I'm not going to say any more about this other than we are picking up those local soil properties if we want to simulate a certain location. We can do that if one wanted to simulate a smaller area. We divide the state and actually the eastern part of Colorado and most of Kansas into what we call farming practice zones. What we're looking at in these practice zones then is how would you produce it differently in those zones. I don't know, I'm guessing Gary's using maybe a 98-day corn or 95-day corn out in the panhandle. You know, guys back in eastern Nebraska probably using, what, 120-day corn. And so we try to depict those differences in production practices as we go across this region. And so we have, for example, we have a tillage file. You can pick. You can kind of define your tillage operations, so you can look at that impact of tillage on residue, because that impacts runoff and evapotranspiration. So you can kind of create your own little typical farmer if you want to out there. We've used the model then, and we've simulate, I don't know, we have about 65 weather stations in Nebraska that we simulate for. We simulated about another 60 weather stations across eastern Colorado and most of Kansas. And we can end up then getting some relationships. This happens to be a relationship in the increase in evapotranspiration from non-irrigated to fully irrigated crops as you go across the basin. And this correlates very well to latitude and longitude, to longitude. And so we're able then, we have 60 weather stations in Nebraska, so we're able then to go and predict what's going on in counties where we didn't necessarily have a location for a weather station to do the calculation. The other thing we have to do is we have to look at where's the water go from my center pivot when I do this simulation. And so we've developed a kind of simple method that we can begin to look at partitioning our irrigation water. We're mostly thinking about a pivot here. We could do gravity, but we're looking at a fairly simple way to look at trying to break up where the water goes. We put together these the evaporation of droplets and the overspray drift, the canopy evaporation and runoff. We kind of lump those into one group called surface losses. It's water that you put on that's not going to infiltrate. The water that runs around in the field may be redistributed. Hopefully we don't have too many pivots that have runoff problems, but if you do have some water running around, we give you the option to reduce your uniformity coefficient on the pivot by, really the way I like to look at it is the uniformity coefficient for the pivot is how well the pivot's designed. The uniformity coefficient for the infiltrations, where does the water infiltrate in the field? And that number can never be better than what it was for the pivot to begin with. So we give a way to estimate that. You know, if I look at all these arrows on here, the only arrow that pays anybody any money is this one right here for transpiration. It's going back to yield. And that's the one that's important to you to try to maximize. We do this just looking at a statistical procedure. I'm not going to bore you with all the details, but what it lets us do is the difference between this blue line and this kind of gray line here is looking at the loss of water at the surface, the water you put on that didn't infiltrate into the soil. So everything above this line here is water that infiltrated into the soil, but we can't be perfectly uniform. And so as I look around the field, some areas of the field receive more water than other areas. And that's what this is showing. So maybe, you know, on average, the depth that infiltrated was about 11 inches across the field, but maybe 20% of the field got more than 13 inches of infiltration. Maybe another 20% received less than about 9.5 inches. So we represent this by some parameters for a pivot. We pick a part of the field. What portion of the field do you want to irrigate to get full yield? That's what we call adequacy. So this example is showing that about 68% of the field would be fully irrigated. So everything to the left of this would add full yield. those things on the right would have had a little bit of water stress. We use that then to break down and calculate where's the water go from the pivot. A lot of data here. Let me go on to the next one. It lets us break down and look then. The solid line would be the amount of water that goes to ET. The closed circles are depercolation that occurs in the field because of non-uniformity or runoff that accumulates in low areas. And then the open circles are the amount of surface loss that we have because of evaporation or some other factor. When we look at the yield, the ET from the field, if we have a linear yield ET model, now then we can also look at how much yield I should get from the field. And we can compare that to what we get using our water optimizer production function. What I'm showing here then is the goal of this, folks, is that when we looked at the uniformity in the field, the question we get sometimes, well, you're using your CROPSIM model and it doesn't really look at how to uniformly irrigate in the field. I'm saying here we get the same answer. We do pretty well until you get to a system that has a large amount of surface loss. So if you had maybe if you had a canal system and you were providing water and there was 20-30% of your water running off a furrow field, we would have to rethink this a little bit. But for center pivots where we're not having that big a surface loss, then we seem to do pretty well. So what I'm really saying is I think our CROPSIM model represents the field, represents that field condition pretty well. So what we do then is this is data for Nebraska from the NASS system. And what this is showing then is we look at this, we use this data to make estimates. We do it on a county by county basis as long as we have data. So in the CROPSIM model, if you wanted to sit down and run a simulation for your farm, you simply pick what your county is, and you should have data in there for most of the crops. There might be a few crops, like if Gary's camelina, you want to raise that in Seward County, we don't have any data there. You're on your own there to put the data in. You can do it, but just be careful how you put the data in, okay? Our goal was to make this so it was available to a lot of people. So we go through a process. We do a little bit of smoothing of this data, not a lot, to make it, we think, reliable across the state. So kind of in summary, we do not simulate yield directly. My experience, I've done that in the past, and my experience is that's a whole big can of worms, and then trying to get back to what producers do is even another second can of worms. So we use an external database. We give you the opportunity in the model to change the yield. If you have yield data that you can show that you're doing better than that default value, then by all means change it. But just make sure you change them all. Don't just change one crop. What we looked at, in essence, what we looked at was 10 years of data. And as I recall, we took out the 3 lowest years out of the 10 years. And we did that to take out any negative bias that might occur to drought. We didn't want to have a drought affecting these numbers. So we kind of looked at the better yields in a period of time, and we used those as our starting spot. We did a little bit of smoothing to be able to, once in a while you get a county to county variation that's a little bit, you didn't quite believe, so we took a little license there. We computed the non-irrigated yields by using the NASS data and some of the results from the crop simulation model to get our values for the non-irrigated yield. Well, we've done that now for all of these green counties that you see here. Data is available to run. In Nebraska, data is available to run all the crops we know something about at this point. In Kansas and Colorado, there's a few less crops that you can run. They don't have quite as good a database in some of those areas. We simulated 1949 through 2009 to get these base data. We did 64 weather stations in Nebraska and about the same number in Kansas and Colorado. We did the simulation for a coarse or a sandy soil, a medium soil, which is like Gary's sandy loam or fine sandy loam out in the Panhandle. And then we did it for a fine textured soil that's like our Hastings and Hall and Hoard silt loams in eastern Nebraska. And so we have database built for those conditions, for those 3 crops in all of the counties across this region. I'll stop there at that point. I don't know if I'm about on time or not. Any questions or comments? I wanted to let you know what we do. Hopefully you can look at our predictions versus field data and say, well, you're in the ballpark anyway. So Jenny's question, if I get it right, is we simulated data from 1949 through 2009. And the question is, are we going to include some more recent data in that analysis? What we're doing, Jenny, is we're not using any one specific year. We use that longer period of record to get the average condition. And so we do not have an option in the model where you could go in and say, I want to look at 2012. Or 2011. So we simulate a long enough period of time that we pick up droughts and wet periods so that our average condition for these responses is reliable. So, we do have periods of drought in there. We haven't put in, but we have not included the last couple of years. If our average is good, 1 year or two shouldn't make very much difference in it. That's a question I get asked a lot. The first question I'm going to ask you is how many gallons per minute do you have for your well and how many acres do you irrigate? Okay, so you're getting about you have about 6 gallons per minute per acre that you can apply out in the field. That's equivalent to about 3/10 of an inch per day if you run it full time. Now, if I only water at night, how much can I put out? I can put out half that, right? So I'm down to 15 hundredths of an inch per day. So the first thing you got to think about, if you want to turn off during the day, do I have enough capacity to meet that crop water requirement if I shut that off? And probably where you're at, if you shut it off for 12 hours, you wouldn't have enough to keep up with crop water use during the middle part of the season. The other thing that we find is that there's not as much savings there as you might think. What happens when we irrigate with a pivot? We wet that crop canopy up. And as soon as we put water in the canopy, we did a big study with some colleagues down in Texas. And as soon as we wetted up the canopy and we got a water film on those leaves, the transpiration rate, that is the water going through the plants, shut off completely, went to zero. And so during the time that the canopy was wet, we had more evaporation because there was free water on the canopy, but transpiration didn't occur. And so there was an offset there in that process. We didn't see as big a difference as you might think. But that offset, maybe the increase in evaporation off the canopy is about, let's say it's about 40% more than what the transpiration would have been had you had transpiration during that time. Now let's think about what happens at night. If I'm in an area like out here in the west where I don't get dew at night, I wet the leaf anyway, and that water's going to evaporate off that leaf, but I don't have any transpiration at night because those stomata of that plant are light sensitive. So the corn stomata close in the dark, okay? So you don't have a compensation there of transpiration reduction when you irrigate at night. So the savings is not as big a number as a lot of people think it. But the first question you got to ask is, do I have enough capacity to do that? And if you don't have capacity, then you're looking at deficit irrigation whether you wanted to or not, in that process.